Okay, we've just done a whole bunch of stuff on linear regression, right? We saw how we could fit one line to data, and then we saw how we could add more variables and interpret regression output. But there's a problem with this linear regression, and that is that the world is often nonlinear, right? So remember I talked about John von Neumann saying the study of nonlinear function is akin to the study of non-elephants, because there's just so many more nonlinear functions than there are linear functions. So if we look out there at the world, we might see data, right, that looks like this, or we might see data that looks like that, right, again, or we might see data that sort of both those features that looks like that. So the question is, how can we use those techniques we've done where we're sort of like trying to fit lines the best we can if the world is kind of messy? So this very short lecture, I just want to talk about 3 ways you can get around this problem that the world may be nonlinear, and we've got techniques that help us sort of understand linear functions. So here's the first thing we can do. First thing we can do is we can just approximate our nonlinear function with a linear function. So we've got this nonlinear function here, right? But we're just going to draw 3 linear functions to approximate it. So that's the best possible approximation. And so what we could do is we could say, I have a model. So in this case, I may have a model that says this is my functional form. This is what should happen. So I want to test and say, well, does that model work? Well, that could be a fairly difficult thing to do. So a shortcut would be to say, well, instead of testing whether that model works, I'm going to test whether these 3 linear models work. This linear approximation comes close. Here's a way to think of it. If you've ever been to Greenfield Village in Detroit, which is near Ann Arbor, they've got a brick wall that's curved, right? It goes just like this. It's a curvy wall. And it's made out of bricks. And the way it's made out of bricks is there's all these short little straight bricks, right? But the bricks are laid in such a way that they make a curve. Well, the same thing can go on here. You can say, my model says the thing should be really curved, but what I can do is I can approximate that curve through some short lines. Now let's push that further to see the second way we can do it. Suppose you got a bunch of data, and the data, you notice when you look at this thing that there seems to be sort of different patterns in different parts. Like it seems to be sort of sloping up in this region, right, but sloping down in this region. Well, what you can do is you can break your data into different quadrants. So you can say, okay, here's the first quarter, second quarter, third quarter. We're just going to assume that like we break it into 4 equal parts. Then what you can do is you can say, okay, what I want to do is I want to create a function that's linear in each segment, right, but explains as much of the data as possible. So here I might start out and say, well, look, here there's not much to explain. It's kind of flat. But now when I get here, the data's down here, so I want to come down. I want to head down in this direction. Now we might think, hey, let's just come way down here. But the problem is if I come way down here, how am I going to deal with all this data up in here? So what I'm going to do is I'm going to say, nope, that's not going to work. So maybe I'll come down just a little bit, right, to try and explain some of this. And then when I get up here, I can start heading up in this direction. Now to get here, right over in here, I don't want to head all the way up into this region because I've got to come back down to deal with this data. So what I'm going to do is I'm going to come up here part way, and then I'm going to head down this way. Now formally this would be called a spline method. But what's going on here is you're sort of fitting different quadrants of the data to different linear functions, and you're sort of coming close to explaining some of the nonlinearity. So 2 things we can do. The first one is if I have a model that gives me a nonlinear function, I can replace it with a sequence of linear functions, the best possible sequence. And then second, if I've just got a bunch of data and it looks highly nonlinear, I can break the data into separate parts, right? And then what I can do is I can fit linear models to each of the parts. Now there's a third thing I can do. Include nonlinear terms. Let me explain what I mean. Suppose our data looks like this. So it looks like it's kind of coming off like the square root of x, right? Instead of writing y equals x plus mx plus b, I could write y equals m times the square root of x plus b. So all I'm doing is replacing x with the square root of x. One way to think of this is I could write this as y equals mz plus b, right? So that's a linear model, but I'm just redefining z to be the square root of x. So again, I'm back to having a linear model. In fact, I could let z be anything I want. I could let z equal x squared. If z equals x squared, right, and I write y equals mz plus b, what that would do is that would fit something that looks like this, where here's y and here's x, where it sort of goes up like a squared tree. So another way I can deal with nonlinearities is just to include nonlinear terms and treat them like they're linear terms. So we've learned 3 things, right? The first is, if my model gives me a function that's nonlinear, I could say, well, let's just replace it with a sequence of linear functions that approximate it. Second thing I can do is if my data looks like it's nonlinear, what I can do is I can break the data into segments and then fit linear models within each segment, and that'll capture some of the nonlinearities. And then a third thing I can do is I can just introduce nonlinear terms. So instead of having x1 and x2, I could have the square root of x, or I could have x squared. I could even have something like the log of x, or the sine or the cosine of x, right? I can do anything I want. I could put any function of x in there in place of x. X is just like a placeholder for some variable. So even though we've thought about drawing lines through data, we can actually draw sort of any function through data. Now the statistics on this and knowing how accurate your coefficients are and that sort of stuff gets more complicated when we start making these changes, but you can still do it. And if you take an advanced course in statistics or econometrics, you learn some of these techniques. What we're trying to do here, though, is just get an understanding of how the models work and what linear models do, and even sort of quote-unquote linear models with nonlinear terms do, is they help us understand patterns in data, help us understand how much of the variation we can explain, and understand what's the sign, what's the magnitude, right, of the coefficient of each of the variables that we think are important. Okay, thanks.